In this video lecture, we continue our examples and discussion on partial differentiation. But now we look at working out at finding the higher order derivatives. Well, we've come across higher order derivatives in the single variable calculus. We found first derivative, second derivative, and we can go on third derivative and so on. Now, how does this play out in partial differentiation? We are not going to go through a formal discussion where we calculate and work out partial limits and theory. Rather, we look at it from a concrete example. So consider the function z equal to 3x squared plus 4xy minus 5y squared. In other words, z is a function of the variables x and y, which means when I find the derivatives, I'll have to differentiate partially, keeping the one constant. From our first video lecture, when we find a first derivative, which in this case must be a partial first derivative with respect to, in our first case, with respect to x, then we have to keep the y constant. Now, you can find a particular way or method of working this out, how you want to approach it. So let's look at the first case. If I want to find partial dz dx, I'll have to ensure that y remains constant when I differentiate. So what I normally do, I first look at each term and look at the first term, 3x squared. Does it contain an x? Yes. Second term, does it contain an x? Yes. The third term, does it contain an x? No. That means 5y squared is a constant. So when I differentiate 5y squared, I will get 0 because there is no x in that term. So let's do that. Partial dz dx. The first term, the derivative of 3x squared with respect to x, that is 6x. Go to the next term, but I just want to double check this next term. There's two terms, x times y. Now, do I use the product rule in this case? No. It would be easier to simply use the single term. So I'll be keeping the y and the 4 a constant. So I'm going to write down plus 4y, because those are my constants. Now I differentiate x, and the derivative of x is equal to 1. So that answer will simply be 4y. Now let's look at the other case. And in this case, we have partial dz with respect to y. So just to make sure that we are not going to repeat or make any mistake, let's erase that. Now I want to look at z, but differentiating partially with respect to y. So let's see which terms contain y. That one doesn't contain y. That contains a y. That contains a y. So this term completely is a constant, and that will give me 0 when I differentiate with respect to y. So let's differentiate. Now, for xy, I'm differentiating with respect to y. That means the 4 and the x is a constant. Put it down. The derivative of y is equal to 1. Minus, and now differentiate 5y squared. That is 10y. There is your first derivatives. Your first order partial derivatives. Now, we need to continue now because we can find a second derivative. However, if we look at both cases, so let's look at one case at a time. Let's look at partial dz dx. The answer of partial dz dx is 6x plus 4y, which means I can differentiate that first order partial derivative either with respect to x or with respect to y. So let's choose the first one. In other words, let's differentiate this partial derivative of z with respect to x with respect to x again, in other words, the second order. So look at the notation. That means I want to differentiate partial dz dx with respect to x. How do I write that? Partial d2z partial dx squared. So watch the notation. When you see that, that means differentiate with respect to x once and again twice. Now, how do I go about that? Very easy. This is the first partial derivative with respect to x. Now I differentiate that answer with respect to x again, following the same pattern. Look at 6x. What's the derivative of 6x with respect to x? 6. Look at the second term. Does it contain an x? No. Therefore, the derivative of that with respect to x is equal to 0. That's right. So your answer for d2z dx squared is equal to 6. Now, let's continue. I have dz dx. I differentiated it with respect to x. Now I want to take dz dx and differentiate it with respect to y. So I'm going to look at partial dz dx. It contains 6x plus 4y. And the derivative of 6x, because there's no y, is a constant. Therefore, that will give me 0. So now I must look at 4y. The derivative of 4y with respect to y is equal to 4. And that is indicated. Look at the notation. Partial d2z, partial dy dx. However, when you see this second order mixed partial derivatives, so these are what we can call our second order mixed partial derivatives. Why mixed? Because you are finding partial dz, then partial dz dx, then partial dz dy. Unlike this case, where you're finding the second order partial derivative with respect to x only. However, notice this and that. When you're asked to find partial d2z, partial dy dx, you do that one first, like we did, and then the y. So just be careful of the notation. Now let's go to partial dz dy and do this likewise there, but now with respect to y. So partial dz dy, differentiate again with respect to y. In other words, d2z dy squared. Because there's a 4x, there's no y, this whole thing is a constant. That 4x will give me 0. Then look at minus 10y. The derivative of minus 10y with respect to y is minus 10. Now go to the mixed order partial derivatives. Look at partial dz dy, which you've calculated. There's it there. Now differentiate that with respect to x. The derivative of 4x with respect to x is 4. The derivative of 10y with respect to x is 0. Therefore, your answer is 4. And that is the procedure that you could use to find second order partial derivatives. Now, make a note over here. Note this. All your cases, look at this answer and that answer. They are the same. With any function you get, you will notice that when you differentiate partial dz, d2z, partial dy dx, and partial d2z, partial dx dy, you will always find that they are equal. That is a theory that you can prove, but we are not doing any proofs at all. So you'll always find that the mixed second order partial derivatives are indeed equal. Okay, that was an example for discussion. Now let's look at an example per se. And we are going to find all second order partial derivatives of z equal to x squared sine of y cubed. So let's go ahead. Partial dz dx. So I must look at partial dz dx. That means keep y a constant. And there's sine y. All that will be a constant. I will write that down. Sine of y cubed. Now find the derivative of x squared. What's the derivative of x squared? 2x. That's it. Let's find partial dz dy. Now x squared is the constant. The x is a constant. Put the x squared down. And now find the derivative of sine y cubed with respect to y. And there I'm going to use the rule. First the sine, that gives me cos of y cubed, then the y cubed, 3y squared. So that answer will be x squared. Can I just put the 3 here one time? X squared, y squared, cos of y cubed. So that's your first order partial derivatives. Okay, let's find the second. Partial d2z dx squared. What does that mean? It means take that one and differentiate that answer with respect to x. So if it's with respect to x, you will leave the sine y cubed because that's a constant and differentiate 2x. What's your answer? 2. So the second partial derivative of z with respect to x, in other words, partial d2z dx squared is equal to 2 sine y cubed. Now, the mixed order partial derivative d2z partial dy dx means I must look at this answer, but differentiate with respect to y. So 2x is the constant. Now differentiate sine y cubed with respect to y. First the sign, so it's cos. Derivative of sine is cos y cubed. Remember, the argument doesn't change. We don't stop there. Now we differentiate the chain rule, 3y squared. And that can be simplified. 3 times 2, that gives you 6 x y squared cos of y cubed. Second order mixed partial derivatives. Now, let's have a look at our second order partial derivative with respect to y, and watch this one very carefully. So if I want to find d2z dy squared, I must look at this answer and differentiate this partially with respect to y. But notice there's a y squared and there's a cos y cubed, and they are multiplied, which means I must use the product rule. And now you bracket in such a way that you can use a product rule easy. And I would suggest bracketing, if I can just change the color, let's just go for a blue, bracket here and there. Now I can differentiate using the product rule. And I'm differentiating with respect to y. So if that's my f and that's my g, in the f, I'm differentiating with respect to y. So 3x squared is the constant. Leave that. Differentiate y squared, and you'll get 2y. And of course, you multiply that with the cos of y cubed without differentiating. Now you add plus. Now you leave the f, 3x squared y squared, and you differentiate cos of y cubed with respect to x. Let's see. What do we get? What's the derivative of cos? Minus sign, and you do not change the argument. Do you stop there? No. Times the derivative of y cubed, which is 3y squared. And of course, I can simplify, or can I simplify? Well, I would suggest just take out a common factor. A common factor here is 3x squared y. I'm left with 2 cos of y cubed minus 3x squared. Oh, we're taking out 3x squared y, so we can be left with here 3 y cubed sine y cubed. There is your second order partial derivative, partial d2z dy squared. Okay, just to double check that, common factor 3x squared y, I'm left with 2 cos y cubed, and here 3x squared y, I'm left with 3 the y cubed sine y cubed. Now let's check. I need now to work out the second order mixed partial derivatives, which means I first differentiated with respect to y, which is that answer there, and now I'm going to take that answer and differentiate with respect to x. So if I do that, then all the other terms, and I'm just going to do it over here so that we can see it a lot better. partial dz dy was 3x squared y squared cos of y cubed. And if I want to differentiate now this answer with respect to x, y squared cos y cubed and 3 is the constants. So they must all go down. The 3, the y squared, the cos y cubed, they are constants. Now I differentiate the x squared and I get 2x. Multiply that out. 3 times 2 is 6. X y squared cos of y cubed. There's your second order mixed partial derivatives. And what do you notice? That's right. They are equal. So that will be correct. Next example. Typical of the types of problems that you get with partial differentiation. Proving an equation using notation correctly, understanding what it means. So here I'm asked to prove that partial d2v dx squared plus partial d2v dy squared is equal to 0. What does that mean? I cannot find partial d2v dx squared immediately, because that comes from finding the first partial derivative and then differentiating again with respect to x, which means in both cases I must first find the first partial derivative and with respect to x. Now let's look at the function. V is equal to the ln, and inside the argument is x squared plus y squared. So we're going to do the chain rule. First the ln, 1 divided by the argument x squared plus y squared. Then we don't stop there. Now I'm differentiating with respect to x. So the derivative of x squared is 2x, and because I'm differentiating with respect to x, that will give me 0. There's my first order partial derivative with respect to x. Let's continue immediately. Partial d2v dx squared. Now I must differentiate this answer with respect to x again. And I notice there's an x in the numerator and denominator, which means I must use quotient rule. So let's use the quotient rule correctly with respect to x. So take the denominator and square that. X squared y squared all squared. Now let's leave the denominator x squared plus y squared and differentiate the numerator with respect to x. We notice there's a 2x, so that will be times 2. Then minus, now I leave the numerator and differentiate the denominator with respect to x. X squared, the derivative there is 2x. What about y squared? That derivative should give me absolutely 0. Because y is the constant, I'm differentiating with respect to x. Okay, let's just multiply out here. 2 times x squared, 2x squared, 2 times y squared, minus 4x squared. Divide that all through by x squared plus y squared all squared, and I get an answer 2y squared minus 2x squared. Divide this by x squared plus y squared all squared. Okay, now we have the first part. Now let's work on the second part. partial dv, partial dy, partial derivative of v with respect to y. Right. So now it will still be ln and x squared plus y squared, but in this case, x will be the constant. So it will be 1 divided by x squared plus y squared, multiply this bracket with respect to y. That means x is a constant. The derivative of y squared will give me 2y. Notice very, very similar to our first partial derivative with respect to x. Now let's continue. Partial d2v dy squared. So it's virtually the same. There's a y in the numerator, y in denominator. I'm going to use the quotient rule. Put the denominator down. You're going to square that. Leave this. But now differentiate with respect to y. The derivative of 2y, that's 2. Minus, then you leave 2y. Differentiate the denominator with respect to y, 2y. Multiply that out. I'm just going to give the answer immediately. That will be 2x squared minus 2y squared. Divide that by x squared plus y squared all squared. Now let's put that together. Therefore, partial d2v dx squared plus partial d2v dy squared is equal to, what's the second partial derivative with respect to x? 2y squared minus 2x squared. Divide that by x squared plus y squared all squared. Now we are going to add x squared plus y squared d2v dy squared 2x squared minus 2y squared. Do we need to go any further? The LCD is the same. Add the numerators. 2y squared. Oh no, sorry. 2y squared cancels with 2y squared. 2x squared cancels with 2x squared. Your answer, 0. So there, guys, your second order partial derivatives. Can you see how important it is for you to know your differentiation rules and your procedures? And very importantly with partial differentiation is your notation. Partial d2y, partial d2x squared, partial dv dx, partial dz dy squared. Look at how they ask the questions. That is very, very common in partial differentiation. That brings this lecture to an end.